Lesson 22 demo. Today we'll learn the derivative rules for logarithmic functions and inverse trig functions. Number one, last class we reviewed the following fact: e to the ln of x equals x. Let's create a formula for the derivative of ln of x. Now, unofficially, I provided you with this formula back when we were learning the chain rule, just so we could have an opportunity to practice more varied chain rule examples. But this is where we will formally learn the derivative of ln of x. So we're going to start with the equation that was given up there, e to the ln of x equals x. I believe this is something that is true for all x. And then we are going to take the derivative of both sides of this equation. So I'm going to put dbx in front of both sides. So I started with an equation that's true. We're doing the same thing to both sides, and we will get a resulting equation, which is also true. Okay, the right-hand side is easier. Let's start there. The derivative of x, that's just, that's just 1. But the left-hand side is tougher. This is e to the stuff. Now, we know how to do the derivative of e to the stuff. It is e to the stuff times the derivative of the stuff. And the stuff in this case is that power, ln of x. So that was e to the stuff, and then times the derivative of the stuff. Now, we don't know what the derivative of the stuff is. We're actually calculating the derivative of the stuff in this example right here. So let's get this derivative of the stuff by itself by dividing both sides by e to the ln of x. So the derivative of ln of x must equal 1 divided by e to the ln of x. But e to the ln of x is simply x, right? That's one of the properties that we saw last class. So therefore, the derivative of ln of x is 1 over x. And this is something that, again, I shared with you informally in a previous class, but now we've got it officially. We see why it must be true. So we'll fill in the blanks here. Derivative of ln of x is 1 over x. And then the chain rule says the derivative of ln of stuff must be 1 over the stuff times the derivative of the stuff. And I'm making a point out of writing this derivative of the stuff higher. It is up on the numerator if you decide to make a single fraction. It is definitely not downstairs with the stuff. Okay, the above derivative formulas are miraculous. Here's what they say about slopes of tangent lines of f of x equals ln of x, which is pictured below. Suppose that we go to, for example, x equals 4 on this curve right there. And we draw the tangent line at that point. The slope of that tangent line, according to our formula, is just 1 over x, right? The derivative of this ln of x is 1 over x. And so let's try that tangent line again. One more time. That's looking good. So the slope of this one at x equals 4 must be 1 over 4. It's just 1 over x. And if you were to move over a little bit to x equals 10, and you were to draw the tangent line at x equals 10, so this one's going to be very flat, but the tangent line slope here is 1 over x. The x in this case is 1/10. So you go to whatever number you want to on the x-axis, you go up to the curve, the tangent line at that particular point has slope 1 over whatever your x coordinate was. It is amazing. And it works also for numbers between 0 and 1. So for example, if I go to the curve at x equals a half, it's kind of hard to see, but I'll say like right here, that this is x equals a half. And I will draw my tangent line. And the slope of that tangent line is 1 over the x coordinate, 1 over a half, or said another way, 2. Okay, number 3, let's find some derivatives. ln of stuff. We just saw that the derivative of ln of stuff is 1 over the stuff times the derivative of the stuff. And again, highlighting that 3x squared minus 7 is decidedly not on the bottom. It is on the top if you wish to make it a single fraction. You don't need to, but I'll just write it one time here. 3x squared minus 7 over x cubed minus 7x. Okay, part B, this is ln of x to the 7th. This is some stuff to a power, so the power comes down. You copy your stuff one time, subtract 1 from the power, and then multiply by the derivative of the stuff. Derivative of ln of x is 1 over x. And number 4, we're going to create a formula for the derivative of inverse sine. I don't remember. I don't think I gave this one to you unofficially the other day, so this will be brand new, but we're going to figure it out from scratch. And the way we're going to do that is by taking a derivative of both sides of this equation. We know that sine and inverse sine cancel when they look like this, so we should believe that sine of inverse sine of x is simply x. So let's copy that equation again. Sine of inverse sine of x is equal to x, and that's an equation that's true. So then if I take a derivative of both sides, I should also get an equation that's true. Again, the right-hand side is easy. The derivative over here is just 1. The left-hand side is trickier, but we can do this. This is sine of some stuff, and we know already from a previous class that the derivative of sine of stuff is cosine of that stuff times the derivative of the stuff. The stuff is in here. Now, I don't yet know what the derivative of inverse sine is, so we're just going to write it symbolically times the derivative of that stuff, inverse sine of x. And I'm trying to calculate a formula for the derivative of inverse sine, so we're going to take this equation and divide both sides by this part, which will get the derivative of inverse sine by itself, and we will largely be done, although we are going to simplify a little bit. Okay, so there you go. Brand new formula. Derivative of inverse sine of x is 1 over cosine of inverse sine of x. Now, this is a perfectly good answer. It's a full credit answer. It's correct. It is a valid derivative for inverse sine, but I will tell you that most of the mathematical community does not use this as the derivative of inverse sine. We're going to use an alternate version of this thing. So here's how we're going to calculate it. We are going to focus on cosine of inverse sine of x. And in particular, I'm going to let theta equal this thing right here. Just to give it a name, and theta is a good name for it, right? Because then I'm really talking about cosine of theta, so that makes sense, right? It's an angle. Inverse sine of x is an angle. And so going back to that purple equation, if theta is inverse sine of x, then I can take the sine of both sides and equivalently write sine of theta equals just plain old x. So that's taking sine of both sides. And now I can draw a right triangle with a theta in it. And I know that the sine of theta is supposed to be opposite over hypotenuse. That's an old trig fact. And so if I want to really force sine of theta to look like a fraction, then I guess I should divide by 1, right? And now I can label my right triangle there. Opposite is supposed to be x, so the opposite of theta is over here. There's my x, and the hypotenuse of this right triangle is 1, and then I can label the other side of this triangle using Pythagorean theorem. So when you do that, it might take a couple of steps, but we should get 1 minus x squared inside of a square root. So what good is all of that? What does that have to do with our original answer? So take a look again. 1 over cosine of inverse sine of x. But we just did some renaming here. And cosine of inverse sine of x, which was our denominator, is really just the same as cosine of theta. So if I can just read cosine of theta from this right triangle, then I will put whatever I get right down here instead of this denominator. So I'll put an orange here, equals 1 over, and according to my right triangle, I know that cosine of theta is adjacent over hypotenuse. So looking at this orange right triangle, the adjacent side is square root of 1 minus x squared divided by the hypotenuse. Hypotenuse is still 1. And so we just get 1 over square root of 1 minus x squared. And that is the version of the derivative of inverse sine of x that is much more common. And that's going to be the only one that we use. So number 5, derivative of inverse sine of x is 1 over square root of 1 minus x squared, which we can then apply the chain rule to. Inverse sine of stuff, the derivative of that is 1 over the square root of 1 minus, but then instead of x squared, it is stuff squared. But then at the end, times the derivative of the stuff. And again, note that I am intentionally putting this above That derivative of the stuff for sure is on the top if you're going to make a single fraction. It is not downstairs. Okay, you can use a similar technique. We're not going to do it out, but you can show that the derivative of inverse tan of x is 1 over 1 plus x squared. We did see that informally a few classes back. And therefore, the derivative of inverse tan of stuff is 1 over 1 plus the stuff squared, and then times the derivative of the stuff. Okay, so let's put our new derivative rules to use here in number 7, finding the derivative of inverse sine of 8x squared over arctan of x cubed. First and foremost, this is a quotient of two functions of x, so we must use the quotient rule. So here we go. Big fraction, denominator gets squared, we'll start there. Be really careful here, it's not x cubed that's getting squared, it's the entire denominator, it's the arctan that's getting squared. Okay, here we go with the quotient rule. Bottom times derivative of the top. Copy the bottom times the derivative of the top. The derivative of inverse sine we've just seen. Derivative of inverse sine of stuff is 1 over square root of 1 minus the stuff squared times the derivative of the stuff. So we just have to apply that here where the stuff is 8x squared. So 1 over square root 1 minus some stuff squared. The stuff is 8x squared. So 8x squared goes right in here, and it itself gets squared, times the derivative of that yellow stuff, 16x. Again, that 16x is not on the bottom, it's on the top. That's part of the quotient rule, minus the top, inverse sine of 8x squared, times the derivative of the bottom. Okay, derivative of arctan of x cubed. Do we have a formula for the derivative of arctan? Yes, as long as you recognize that arctan is just another way to say tan inverse. And so I put that one here just to refresh your memory that arctan is a synonym for inverse tan. So derivative of arctan of stuff is 1 over 1 plus the stuff squared times the derivative of the stuff. In this case, the stuff is that. So here we go. 1 over 1 plus the stuff squared, in this case it's x cubed, times the derivative of that same stuff, 3x squared. Again, that 3x squared is on top.